Reflections. You guys talked about reflections last year. You guys talked about reflections in the x-axis, which is what we're going to talk about first. Reflection is a mirror image about a line or an axis. Invariant points are points that do not move after transformations have occurred. So invariant points gets asked a lot on the diploma throughout the different units. Invariant points means the point started at 4,1, whole bunch of stuff happened, it's still at 4,1. What it does not mean is it started at 4,1, that 4,1 moved around, and then landed back at 4,1. That's not invariant. Invariant means it did not move ever. It stayed there, it did not change. So, we're going to compare y equals f of x to y equals negative f of x. Okay? So, a lot of the time you guys were given quadratics last year, and you'd be given like y equals negative x squared, let's say. And you guys would say, oh, that's concave down, or it's down because it's reflected, right? And it was reflected in the x-axis. So that means if it was up above the x-axis, it's now down below. It opened down, right? That leading coefficient told you if it opened up or it opened down. Because it's a reflection. If there's no reflection, your parabola is concave up. But if you take all your y values and negate them, which is what a negative in front does, it affects your y's, then your whole graph would be down. Now, we have always had it in like a standard form. But what happens if we have it in this form? So here we have f of x equals x squared minus 4x plus 4. I want you all to graph it on here. So type it into your calculator, x squared minus 4x plus 4. Okay, so we have x squared minus 4x plus 4. I think. There. Press graph, we get that graph, correct? So, do you guys remember how to find the vertex? In this case, what is the vertex? Is it a minimum or a maximum? It's a minimum. So there's no like second trace. The reason why we press second trace is what word is above trace? Calc. So that's when we want to calculate anything, right? So if I go second trace, there is no button for vertex. But there is a button for minimum and maximum. So that is the vertex, right? In this case, it's a minimum. So we press number 3. Then it says left bound, so we have to be on the left side of the minimum, which we are. Enter. Then it says right bound, so we need to move ourselves onto the right side somewhere. Enter. And guess, makes you press enter. So we have a minimum at 2, 0. So our vertex is actually on the x-axis. Now if I just do this, no one knows what the heck each of my lines are worth. I think he's on his calculator. It's just so confusing. Yeah. Just checking. Just keeping you on your toes. Totally fine. So if I just put a dot on there, but I tell you nothing about the lines, a lot of people will go 1, 2, 3. We don't do that. We go x scale 1. That means every tick is worth 1. Y scale 1. Okay? Then we can pull other points off of either side. So if I know it's 2, 0, I can, everyone paying attention, because I think everyone knows this, but then some people are like, what? Did angels just come down from heaven? Like, that's how you feel like when you learn something new on a calculator. So perhaps that's what's going to happen. So you can go second graph and you get a table, which you would move up or down, right? We have 2, 0, so we can pull points on each side. We could do that. Or we can go second trace value, and you can plug in any x and it outputs a y, right? Second trace value. So I know I had 2. I can go 1, enter, and it gets me 1, 1. And then I don't have to redo it. I can now, don't go second trace value again. You can just put a new one in. So I can go 0, enter. And it gives me 4. Now remember that your table of values are whole numbers, right? So could I go like 1.5 and then get that, 0.25? I can get a ton of points, coordinates, correct? 0 is 4. I already did that. Negative 1 is 9. Yeah. And then the great thing about quadratics is they are symmetrical. So they'll look the same on the left and on the right. Please don't make your quadratics pointy. Ooh, that was a badly drawn point. It's supposed to be. All right. Now the key thing, we talked about mapping, right? Did we talk about mapping yesterday? Mapping was to move coordinates, correct? Okay, so this one says write the equation that represents that. We'll do that in a second. I want to use mapping here first. So xy becomes. Now remember, I told you the only thing that affects the x is if there's something with the x. So I go look in the equation. Here's my equation. I'm going to write it right here. Y equals negative f of x. Right? What's with my x? Nothing. So for my mapping, that's going to remain an x. Nothing happened to it. We agree? A lot of people are like, I don't know if the negative goes with the x or with the y. Is the negative with the x? No, so it doesn't go with the x. Literally. That's it. If it's in the bracket with the x, it affects the x. If it's not, it affects the y. So what's being negated? The y. Now, a lot of people go into memorization techniques. So one of the reflections is going to be a reflection in the x-axis, and one of the reflections is going to be a reflection in the y-axis. We're going to have both reflections this year. Okay? Let's not memorize. Let's understand. If my y's are being negated, and I know they're being negated because my x doesn't have anything with it, right? So I know my y is being negated. Let's pay attention. Here's the x-axis, right? If my coordinate is up here, what's my y? Positive. And if I negate it, what's it going to be? Negative. It's okay. That happens at least once every twice or 10 times a day. It's a negative. And if it's a negative y, what's it going to become if I negate a negative y? Everyone's paying attention so we understand, we don't memorize? It's going to be positive. So positive y's will become negative. Negative y's will become positive. What axis am I reflecting about? The x-axis. We agree? So do I have to memorize? People are like, okay, so if it's with the y, it's about the opposite axis, so it's going to be in the x-axis, or maybe it's the y, and then they're confused, and then they write random stuff because they're trying to memorize. Think about it. I'm negating my y's. So if my y is here, it's going to be down here. If my y is here, it's going to be up here. Oh, that's the x-axis. If we understand, we will not make mistakes, because you understand. You don't be like, oh, which axis? Oh, it's the opposite one, and that's how I have to, right? Understanding why. Because your y's will always negate. So if it's positive, it's negative. If it's negative, it's positive. It's reflecting on that x-axis. Okay? So if I take this, I know it's going to reflect in the x-axis. But remember, whenever I move coordinates, I can just plug it into my mapping. So if I take negative 1, 9, what's it going to become, guys? Negative 1, negative 9. I'm going to use a different color. Negative 1, negative 9. What axis is it reflecting in? Yes. Right? And then I use 0, 4. It's going to become 0, negative 4. Then I have 1, 1. It's going to become 1, negative 1. Then I have 2, 0. It's going to become what? 2, 0. What is this coordinate? Because it stayed the same. Fancy, it is the vertex, but what is this coordinate? Because it stayed the same. Because this stayed the same, this is the invariant point. Now, some people ask, well, what if I move one of these points and it lands on one that was there before? Well, did it move to land on it? Yes, so it's not invariant. Invariant means it doesn't move. Okay, then I have 3, 1. It's going to be 3, negative 1. This blue box is just so fun. And then I have 4, 4. It's going to become 4, negative 4. This crosses the coordinates. That one I didn't do. If that was a test, I would be erasing that and making sure that line goes through. It's just hard on the smartphone. So do we see that that's a reflection? Now, if my original was y equals f of x, then I could write y equals negative f of x as the transformed, correct? Remember how we did an example 4 yesterday and an example 8 yesterday? I made you do example 8 right after example 4. Example 4 was y equals f of x, and then I applied transformations to y equals f of x. You just were done. But example 8 was equations, like y equals x squared, y equals 10 to the x, y equals root x, and we had to apply the x's into the actual place where the x's were and the y's to that. Same thing here. So this original, if it was f of x, I would be done. But they're telling me the original is actually f of x equals x squared minus 4x. Do you see that? So if I have a reflection in the x-axis, it has to apply itself to the y. So we have y equals x squared minus 4x plus 4. There's two ways I can do this. I can either apply the negative right to the y in the front, or I have to apply the negative to everything else. And the reason why, I'm going to keep going, and then I'm going to do that anyways, is I have to get this negative over here. I want to get it into y equals. We agree? So I'm going to go negative 1, and then I'm going to divide this whole side by negative 1. When I divide the whole side by negative 1, it affects every single one, doesn't it? So I'm going to end up with y equals negative x squared plus 4x minus 4. This is the actual transformed equation. Type that one into y2. Don't take out your y1. Type that one into y2. Negative x squared plus 4x minus 4. So, everyone paying attention? If you have the fancy calculators like mine, they're different colors. You can physically see the blue was the first equation, the red was the second, right? So I know which one's which. If you don't have the fancy calculators that are colored, everyone paying attention? Because once I press graph, they just draw together, right? The first time I put in equations and I press graph, it'll always draw the first one, then it'll draw the second one, then it will draw the third, etc., right? But after that, if I press graph, they both just pop up, okay? Now, I know which one's the second, but sometimes it's just a quadratic by a quadratic, and I'm like, I don't know which one was first, right? So what I would have you do, I can, because mine are blue and red, but what you do is, everyone paying attention if you don't have the color calculators, you're going to arrow over to this slash. You don't have a red, you just have a slash, okay? And then you're going to hit enter. And it makes the thin slash a thick slash, right? Then press graph. So your first graph will be a thin line, and then your second graph will be the thick graph, and then you can tell them apart. Now there's going to be some of you who are not going to pay attention to me for the next 10 minutes because you're going to be pressing the enter to see how many different things you can get. There's dashed lines, there's shaded lines. You shade to the left, shades to the right, so shades greater than, shades less than. There's little key looking symbols. I've just ruined it for you. Those are all the things that are there. They're absolutely useless. Please don't sidetrack the next 10 minutes trying to figure out what else they look like, okay? So that's going to happen. I'm not for sure. All right. So that's what I do to get thicker and thinner. So state the coordinate of the invariant point. What was it? 2, 0. Now, guys, why did it remain invariant? Yeah. The y was 0. And what we're doing is we're actually... Put down the calculators. Stop pressing the buttons. All right. So you have 2, 0 here. And when we do mapping, mapping is x, comma, negative y, right? So all of our y's are being negated. So every single time our y is anything but 0, it will change. So if it's 4, it would be negative 4. If it's 1.76, it would be negative 1.76. If it's negative pi, it would be pi. Correct? But if it's 0, negative 0 does nothing. So we get invariant points when we have a reflection in the x-axis when our y's are 0. Right? Because 0 times negative 1 is still 0. So how does the graph of negative f of x compare? It's called a reflection in the, which axis? X-axis. Here's the graph of f of x. I want you to sketch the graph of y equals negative f of x. You're sketching a graph. What should you use? Mapping. So the key thing here is we're moving coordinates. We move coordinates. We do mapping. So it's going to be x, y becomes, and people are like, I don't know which one's negated. Well, x is by itself, and it has nothing done to it. So x is fine, and the y is negated. All right. We need to at least pick the minimum point off of each arm. So I'm going to pick that one, this one, or what I'm going to choose. So I have 1, 2, 3, negative 4, 0 is going to become negative 4, 0. Weird, it stays the same. This one's also going to stay the same, correct? Because that's where your y's are 0. We agree? And then we have negative 1, 4. So it's going to be negative 1, negative 4. Now, did I do the absolute maximum number of coordinates you could do? No. Would it be more accurate if I used more coordinates? Yeah. So on a test, the more coordinates you use, the more accurate your graph. Right? All right. Then we're going to flip over to the new page I gave you. Okay, what the heck? Okay, this one's reflections in the y-axis. So if we look here, we have f of x and then we have f of negative x. All right, is the negative with the x this time or not? Yeah, so what's it going to affect in mapping? The x. So if it's with the x, it affects the x in mapping. If it's not with the x, it doesn't affect the x. Literally, that's all it is. So we're going to get, for our mapping, xy becomes negative x comma y. What's going to happen this time? If I have a coordinate here, say it's 2, 2, it's now going to be negative 2, 2. So what? And if I have negative 4, 3, now I'm going to have positive 4, 3. So I'm reflecting in that x-axis. So we're drawing that same original graph. So it was 2, 0, here, here. That's not true. It's not there. And where I messed up last one is I didn't label my graphs like a silly human. That was y equals f of x. I have to label my graph, and I have to say x scale 1, y scale 1. So let's try our coordinates. We're going to get negative 1, 9, and it's going to become negative, and negative 1 is positive 1, 9. So it was here, it's here. That's for sure reflection in the y-axis, right? If the y-axis was a mirror, it's reflecting on it. Now I have 0, 4. It's going to become negative 0, 4, which is just 0, 4. So what is this now? Invariant. Why is this one invariant now? What is 0 this time? X is 0, correct? And we're multiplying x's by -1, so the only place they're going to stay the same is if x is 0. Okay, then we have 1, 1. It's going to become -1, 1. 2, 0. It's going to become -2, 0. 3, 1 is going to become -3, 1. 4, 4 is going to become -4, 4. Now I told you we have to know our stuff really well because we've done horizontal and vertical translations by themselves, right? Now we've done reflections on each axis by themselves. On Monday we're going to do stretches, and then we're going to put them all together. So we need to know our stuff backwards and forwards. So we're actually going to do C and D first, and then we're going to go back up to A because the equation's a bit different. So it says to state the coordinate of the invariant points. Well, there's only one. It's 0, 4. And it's invariant because x is 0, and when I multiply 0 by -1, it does not change. And we talked about this. How does the graph of y equals f negative x compare to the graph of y equals f of x? It's a reflection in the what? Y-axis. It's always the opposite axis. You can memorize that if you'd like, but it's way better if you actually understand why it is in the y-axis, because your positive x's become negative and your negative x's become positive. So you have this like reflection, this flip over that y-axis. If you guys actually know why instead of memorize, your life will be aggressively better in third reduction. Okay. Then I want to go back up to this one. Write the equation. So, in the previous ones, we just put a negative in front of the x, correct? Or we just added 4 to the x we had. Because in the previous lesson, every single example had one x. Yes? How many x's does this one have? There's 2. And both of them need to be replaced with negative x, not just the one. So remember, when you have a reflection in the x-axis, your y needs to be replaced with negative y. Okay? If you have a reflection in the in the y-axis, your x's all need to be replaced with negative x. If there's one x, usually there's only one x. You go to that x, you replace it with negative x. Done. Right? But if there's more than one x, you have to do it to all the x's. So I'm going to have to go, y equals, and then I get negative x squared minus 4 times negative x plus 4. So I'm taking all the x's, I'm using replacement notation, right? Taking the x's and tossing them away, and I'm replacing them all with negative x. So last time I just replaced the y with negative y, and then I divided that -1 over, which applied it to every term. Okay, so here we have y equals x squared, negative 4 times negative x is plus 4x plus 4. Now, if the equation has an f in it, you just hope you did it right. If the equation doesn't have an f in it, you can plug it into your calculator, correct? So can I not plug x squared plus 4x plus 4 into my calculator and see if it reflects it in the y-axis and check myself? Yep. So I'm going to go to y equals, I'm going to clear this one out. The moment you clear it out, it takes away that thick line. So if you want that back, you have to put it back. X squared plus 4x plus 4. And I know I'm right. I walk away happy, right? So if the equation has an f in it, you can't plug it in. But if the equation doesn't have an f in it, you should plug it in. You should see what it looks like. See if it confirms what you found. Because what people will do is they'll find the new equation and then they'll just send it and hope for the best. But if they actually punched it in, they would see it doesn't actually reflect in the y. Go back and try and figure something out, right? See where you made loops. This one did, so we know we're good. So here I've given you a function, correct? The function is f of x. Does this function have an equation that correlates to it? No, it's just a function. Here's a function. It passed the vertical line test. I draw vertical lines, poof, it passes it. I want you to draw the new graph for this one. What's happening here? This is a reflection in the what? In the x-axis. Your moving coordinates, what should you use? Starts with an M. Mapping. And then this one makes all my x's negated, so it's a reflection in the y-axis. Go and try it out. So this one here is going to be xy becomes what? X what? And it's a negative y, not a negative x, because look what my x is doing. My x is doing absolutely nothing. So my x stays x. So if it's with the x, it affects the x. If it's not with the x, it doesn't. It's the easiest way to do it. Okay? And this one will be xy becomes negative xy because it's with the x. Didn't say to state invariant points, but I'm just proving a point about the invariant. When you're done, you're going to flip over. So we're trying out 5, 6, and 7. 5 wants an equation and then mapping. 6 wants the equation. 7 wants the equation. This one says write the equation of the image of the given the following image of. Nope, the image given the following. There's an extra of in there. Then state the mapping notation. So after reflection in the y-axis. So if it's a reflection in the y-axis, it affects the what? How do I reflect in the y? I'm changing the x's. I'm negating the x's, right? So I'm going to get y equals 10 to the negative x. That's it. And then my mapping is going to be xy becomes negative x comma y. Now if I want to reflect in the y-axis, or sorry, the x-axis, I want to reflect in the x-axis, what's changing? The y's. And if we don't know, think about it, just put a coordinate anywhere. Here. I want it to reflect in the y. It needs to go, or sorry, x. It needs to go here. So say that coordinate is negative 4, 2. It's now going to be negative 4, negative 2. Oh, the y's are being negated. Like you can throw a coordinate up there and like compare it if you so choose, right? So if our y is being negated, we can go like this. Or we can divide the negative 1 over. Divide negative 1 over. And give y equals negative root x. Both of these are correct. They'll often have it in y equals though. So they'll often have it in the second one. So it affects the y's. So we're going to get xy becomes x negative y. So this is a reflection in the what? X-axis. It's always the opposite, right? So if it's with the x, it's in the y-axis. If it's in the with the y, it's in the x-axis. So this is a reflection in the x-axis. My brain halted. And then that has to go with the y. So I'm going to go negative y equals root x minus 2. Divide by negative 1. It just sits in front. Y equals negative root x minus 2. B is a reflection in the y-axis because with the x. So it's going to, all of my x's are going to be negative x. So I have y equals square root. That negative x gets tossed and replaced with negative x minus 2. Nothing happens to the 2 because it's just affecting the x. And this one was easier because it only had one x. The other equation we did had more than one x, so we should replace all the x's with negative x. Okay, this one we have a reflection in the y-axis. So to reflect in the y-axis, we have to do this, which means what's negated? The x's. So I know that's the same as saying f of negative x, if you need to do that to help yourself out. But it's going to have to go into that equation. So we're going to get y equals negative x squared plus 1, which is actually x squared plus 1. It's the same equation. How is that even possible? Well, the equation x squared plus 1 actually has a vertex at 0, 1, and it goes, stop it, and it's symmetric. Nope. Come on. I don't have time for you. Do not. I don't want to insert sound. Symmetrical about the y-axis, correct? So if I reflect in the y-axis, this arm is going to land on top of that arm, and that arm is going to land on top of that arm, and I'm going to get the same graph. So people will tell me the whole graph's invariant. Is the whole graph invariant? No. This arm went on top of that one. That arm went on top of that one. This is the only invariant point. We agree? Because those actually moved. Like I said, if the point is still there, it does not mean invariant. Invariant means did not move. It was there. I did a whole bunch of transformations. It remained there. Okay? And then the last one, we have to replace our y. It's a reflection in the x-axis. And then divide by negative 1. So I get y equals negative x squared minus 1. Now these, remember, do those equations have f's in them? Do these equations have f's in them? No. So could I plug that into y1, plug this into y2, and see if they do what they're supposed to do? Yes, reflect in the x-axis. If they don't, you made a mistake, right? You can check these. You can check the ones that don't have x in them. All right, you have the start of the homework from yesterday. I have one page. It is literally only three questions long. So you have yesterday's start of the homework. It's 3 questions long. So number 1, here's number 2, 3. Don't complain about too much homework on a weekend. Couldn't be nicer, honestly. I was going to make it longer. I was like, nah, we're good.